Okay, so our next speaker is Christina Patricola, who's visiting here from Lawrence Berkeley National Lab. She's been there since 2016. She did her undergrad and graduate degree at Cornell University and did a postdoc at Texas A&M for a bit, and has been working at this Department of Energy lab at Lawrence Berkeley. Christina is really pushing the limits of understanding the weather-climate connection through simulation and high-resolution simulation. She has access to some of the state-of-the-art models and computers at this DOE lab, and I think she's probably going to talk about that in today's work, so thank you for coming, Christina. And take it away. I'll give you 5 minutes, warning minutes.
All right, thank you so much, Amy. Good morning, everyone. Can you all hear me?
Yes.
All right. Well, it's a pleasure to be here. So today I'm going to be talking about anthropogenic influences on major tropical cyclone events. And much of this is work that I have done with Michael Weiner, who is also at Berkeley Lab. So just to start off with an outline, so I'm going to be looking at this from an event-based perspective. Looking at both the attribution side of things, so looking at how much climate change may have influenced some particular tropical cyclone events, as well as looking into future projections. And I'm also going to be talking about this in the context of the various approaches that are out there for attribution and projection. And so going through some of the different types of methods, as well as the advantages and challenges or uncertainties that may be associated with them. All right, so these are really the big questions and why many of us are here today. So just to sort of start off with those, how has climate change so far influenced tropical cyclone activity? And as you can see down here at the bottom, there's been quite a bit of work on this, as we just heard from Tom as well. So far there's been no detectable or conclusive trend in the number and intensity of tropical cyclones. And this has to do with, there's just a lot of variability in the climate system, as well as some data sampling issues going from the pre-satellite to post-satellite era. And then we're also interested in how climate change is expected to influence future tropical cyclone activity. And so far, there's been no consensus on projected changes in global frequency, but the climate models and theory are suggesting that we may see an increase in the number, or at least the proportion, of intense tropical cyclones. All right, so why is this such a difficult problem to address? Well, there are a lot of influences on tropical cyclones. So, when we're thinking about this problem, it's just as important to think about the natural variability aspects as it is to think about the anthropogenic influence. Because often if it's, there's some balance of those two factors. And then, we have influences that are coming from the atmosphere and the ocean, and these things can act constructively or compensate, so there are thresholds and nonlinearities in the climate system. And some of these influences are operating on timescales spanning from weather to climate, interannual to multi-decadal variability. There are also some issues that we need to consider in terms of data and model quality. The consistent record of observations covers less than a century. We also know that it's difficult for climate models at their typical resolution to represent intense tropical cyclones. So here we're looking at, this is the black dots are from observations, the red are from a 27-kilometer model, which is actually for a global model, that would be considered relatively high resolution. And at that resolution, you might not really be expecting to get category 4 or 5 hurricanes. And then the other thing that we need to consider is that climate simulations these days are typically relying on convective parameterizations, at least for global simulations. So just a little bit of background to sort of put kind of fill people in that may be less familiar with tropical cyclones. This is an overview of some of the favorable conditions for TCs. So some of the things that we need to have warm ocean temperatures at a surface and also down to some depth, and that's because tropical cyclones, the wind field, can mix up the cooler ocean water from the surface, and so there are some feedbacks there. And we also need an unstable atmosphere, weak tropospheric vertical wind shear, because wind shear is not very good for the organization of tropical cyclones and convection. We need a moist mid-troposphere and a system of organized convection to provide what we call kind of a seedling disturbance. And so if we just think about how these factors may be changing as greenhouse gas concentrations are increasing, we know to expect that sea surface temperatures are very likely to be warming into the future. We're already seeing this. And so that alone would work to intensify tropical cyclones. But we know that that's not the only factor that's important. And so the ocean subsurface is also important, so changes in both the thermal and salinity profiles. And there's been some work indicating that those changes may be a dampening effect. And then if we think about the greater warming of the upper troposphere, that could work to weaken tropical cyclones, whereas we also know that the temperature at the tropopause is also important. And so if we have tropopause cooling, that could work to strengthen at least the maximum potential intensity of tropical cyclones. And then projected changes in the vertical wind shear are uncertain, at least regionally. All right, so the questions that I'm going to be addressing today, so we're looking at this from the perspective of recent destructive tropical cyclone events, and I'm going to be using convection permitting climate model simulations. And so I'm looking at this from two perspectives. One is more on attribution. So how did climate change so far influence hurricanes Katrina, Irma, and Maria? And then looking into the future, if similar hurricanes occurred, how could they change? And so this is kind of a conditional setup where this might be something that is perhaps useful for decision makers where if they have a reference storm that they know was particularly impactful for their area, they could say, okay, we know what those impacts were associated with that hurricane. What if a similar hurricane happened 50, 100 years from now? What could it be like? I'm also going to be looking at the uncertainty due to using convective parameterization and really trying to address how robust these findings are by expanding this study to looking at 15 different tropical cyclone events representing all the different basins globally and also looking at multiple emission scenarios. So I just want to say a couple words on attribution and so what we're trying to do here. So the objective is we're trying to quantify the contributions of both natural climate variability and anthropogenic climate change to the likelihood and magnitude of extreme weather events. And so a lot of times when an event happens, I might get a call from reporters and they might ask me, did climate change cause this event? And that's really, that's not the question that we're trying to address here. It's kind of not really the right question to ask. So what we're trying to look at is how much did climate change modify the magnitude and likelihood of a specific event, if it did at all. Oops. Okay, so I'm going to give a brief overview of some of the different methodologies that are out there that can be applied to attribution and or projection type of studies. So some of these are not specific to type of extreme event. Some of them are more specific for tropical cyclones. But yeah, so starting off with observationally-based statistical models. So this is some work by my colleagues at Berkeley Lab, Mark Risser and Michael Weiner. And here they're using GEV distributions for precipitation, where they're constructing these as functions of natural and anthropogenic variables. And so they can use this to look at things like return periods in this particular study, Hurricane Harvey. And so what we need for this kind of methodology is station data that covers multiple decades so that the influences of natural variability, multi-decadal variability can also be considered. And so some of the assumptions that go into this is that any substantial physical influences on the particular type of extreme event are accounted for as covariates in the statistical model. All right, then going to statistical dynamical models. So these can be, the nice thing about these is that they can be applied to produce many, many tropical cyclones at a relatively low computational cost. And the kinds of assumptions that go into them are what kind of variables to use for tropical cyclone environmental favorability. So there's been some really nice work. This on the left is some results by Jiaying Li. Adam Sobel is also going to be talking a bit more about this later. And so they're using this kind of model to represent tropical cyclones. And one of the special things about this result is that they're actually able to reproduce the statistics of rapid intensification well. And that's something that's difficult for the types of regional climate models that I'm using to be able to do. And then here on the right, this is some results from Kerry Emanuel, where he's used this type of model to assess how changes in the probability of the storm total rainfall associated with Hurricane Harvey may change going from the current climate into the future. Okay, so on to the next approach. This is using global Earth system models. And so here, people are going to be producing century-long and large ensembles of simulations. Usually these are, fully coupled, at least atmosphere-ocean, but many times with the other components of the climate system as well. And as we just heard from Tom, these can be used to detect human influences on observed precipitation trends. There's also another way to use these kinds of simulations where you can make adjustments in the model to run simulations that what we call are the factual. So that would be kind of like a hindcast of recent decades, and then the counterfactual. And in that case, it's a hypothetical type of climate where the influence coming from humans has been removed. And so that can be really useful for quantifying changes in the frequency and magnitude of events, especially those that can be represented well with relatively coarse resolution. So things like heat waves and drought. So this panel here on the left, this is some work from Weiner et al., where they're looking at changes in the heat extremes associated with the 2015 heat wave in Karachi, Pakistan. And so some of the challenges associated with this kind of method is that we do have coupled model biases. And some work that was led by a grad student that I worked with at Texas A&M, Wei-Ching Su, she looked at the influence of some of the typical sea surface temperature biases on simulations of tropical cyclone activity and found that they can reduce Atlantic hurricane numbers by up to 50%. So that's a pretty substantial challenge that we're working with here. Another thing that we need to think about is the suitability for looking at intense kinds of storm events can depend on model resolution. And so that's something that depends on supercomputing resources. All right, so now going on to the last method that I'll be talking about. And this I'm trying to be sort of as comprehensive as possible, but this may be, there may be some things that I didn't discuss. But here I'm going to be using regional climate models in what we call the storyline approach. And so here I'm going to be running hindcasts of specific events that have actually happened in nature. And I'm going to be running those with and without the climate change influences. And so this kind of method works really well when we want to focus on an event that we know what the impacts were, and we really want to be able to use that to gauge how we may want to think about our decisions and planning going into the future. And so this also works really well for intense weather events because we can go down to very high model resolution. So here, we can simulate the intensity of major hurricanes. And the assumptions that go into this is that, an event that's similar to the observed event could occur in a different climate scenario. And I would say that that's a fair assumption if we're thinking about hurricanes. If we have one that makes landfall in a particular region, it's I would say fair to say that we could expect another hurricane to make landfall there again in the future. But the limitation here is that we're not considering changes in event frequency. And so, all of these methods taken together, I would say, provide a really nice way to try to increase our confidence in any kinds of attribution or projection statements that we're making. This is when, we're getting similar results from the different methods. That's indicating that maybe there's something really going on here. All right, so I'm going to talk a little bit about the experimental setup for the regional climate model simulations. So I use the WRF model. So like I mentioned, I'm running hindcasts using observed conditions. So I'm prescribing the boundary and lateral boundary conditions from reanalysis here. And for Hurricane Katrina, I looked at a whole range of resolutions going from 3 kilometer with no cumulus parameterization all the way up to 27 kilometer, where I am using convective parameterization. And this is just to give you an idea of what the hurricanes look like in the model. So, 27 kilometer, that's about sort of what we consider high resolution for a GCM. You can see the hurricane looks much more like a hurricane at 3 kilometer resolution, although there are some things like the eye is kind of on the bigger side. And for each of these simulations, I'm going to be running a 10-member ensemble. All right, so if we think about how we can perturb the model to create experiments for different climate states. So what I'm going to be doing is you can take the boundary conditions and initial conditions from the hindcast data, so taking that from reanalysis. And what we do is we still want to have the synoptic setup that led to the hurricane in the boundary conditions and initial condition, but we want to perturb that so that the mean state corresponds to a different climate state. So we did this for both pre-industrial as well as various RCPs at the end of the century. And so in order to do that, we take the mean climate change for temperature, relative humidity, sea surface temperature, all from a GCM. And we apply that to the boundary conditions that we had in the historical simulation. We also, of course, changed the greenhouse gas concentrations as well. All right, so when I was thinking about this, this was right around the time that one of the new supercomputers came available at NERSC, which is at Berkeley Lab. And there was a free period where we had free access to the machine as long as we were sort of a guinea pig. And so I really couldn't help myself. I kind of went bananas on this. And so this is the list of tropical cyclones that I simulated. And what I tried to do here is I was kind of pouring through the records. And for the Atlantic, so I grew up in Boston, well, outside of Boston. In the Atlantic, I had kind of a reference for what some of the big ones were. For the other basins, I read some, kind of reports on what some of the more impactful events were, because I really wanted to, if you live in an area that is impacted by tropical cyclones, I wanted that to be represented in this list. So I did my best to try to achieve that here. And so I ran all these simulations at 4.5 kilometer resolution. And so I have this for the historical or sort of control hindcast, as well as pre-industrial and RCP 4.5, 6.0, and 8.5. And in the end, this turned out to be on the order of about 20 million CPU hours on the supercomputer at NERSC. And so this was not only a major computational feat, but also configuring all of these different regional simulations took some effort, but it was definitely fun, I would say, and worth it. So. All right, so here we're looking at an animation of OLR from the 3 kilometer simulation of Hurricane Katrina. And these red dots are the observed track. And so this is just to kind of give you an idea of what the hurricanes look like in the model. And you can see that it's doing a really nice job at hindcasting the observed track. And so, so going into the main results, So this is the hurricane tracks from observations, as well as the 10-member ensemble of the historical runs from Katrina. And one of the things we wanted to check is to make sure that the simulated tracks didn't deviate too much from the observed track, because once that happens, the hurricane's sensing different environmental conditions and sea surface temperatures, so it's not really the same hurricane anymore. And so that was one thing we checked for as we were doing sort of quality control on the simulations. And same thing, once we're looking at the different climate scenarios. So you can see that, the tracks are pretty close in the different climate scenarios. So, this is suitable for what we're trying to understand. So here we're looking at box plots of the peak 10-meter wind speed from Hurricane Katrina. And so each cluster here corresponds to one of the different resolution setups. And then we've got pre-industrial in blue, historical in black, and going up to RCP 8.5 in red. This horizontal line here is observations. And what we can see is that in each of these clusters, the responses are pretty similar. So not much change from pre-industrial to historical, and then consistent increases as we go into the RCP 8.5 scenario. So one thing that I mentioned is that the model has a really some difficulty at trying to capture the observed rapid intensification of these storms. So here we've got the time series of maximum 10-meter wind speed from Katrina and Maria. What you can see is, the observed is in black, the historical is gray. In the case of Katrina, it is getting up to the observed intensity, but it's happening a little bit late. For Maria, this was a pretty quick rapid intensification, and the model, again, it almost gets there, but it's a lot later than was observed. All right, so here, this plot is what we call a heat map that's kind of synthesizing all of the results. So I basically went through the process that I just showed for all of 15 of these tropical cyclone events. And so this is looking at the changes in peak 10-meter wind speed from historical to pre-industrial, and then the different RCP scenarios. So anything that's red is indicating an increase in intensity from climate change. Anything that's dark gray, I just didn't run that simulation. And there are a couple that are light gray where I had to toss the simulations because the hindcasted tracks were not good enough, which we could probably have a whole discussion on what good enough is, but I'll leave that for later. So essentially what we see here is if we focus on the column on the left, not really very strong responses going from the historical to pre-industrial. And so in the three hurricanes that we considered, we're not really seeing an influence of climate change so far, at least on the wind speeds. Going into the future, we see quite a bit of red. There are a couple of cases where we do see some decreases. Those tend to be storms that were either weak in nature, so Hurricane Bob, like I mentioned, I'm from Massachusetts, so that's why that one's there. And then Hurricane Andrew, even though in reality it was strong, in the model the intensity was pretty weak, and so that's something that we want to look at a little bit more. But overall, we're seeing a robust increase in the hurricane intensities. All right, so as many of us know, rainfall is also a serious hazard when we're thinking about tropical cyclones, and so we also looked at that. And the approach that we took to looking at the rainfall, we really wanted to be careful in this analysis. And so the way that I did this is, I was following, basically essentially taking snapshots of precipitation following the storm, because even small deviations in the track could kind of make it difficult to interpret if we just looked at regional maps. So here we got Katrina at 27-kilometer resolution, 3-kilometer resolution. This is the historical hindcast and the changes so far and into the future. And what we're seeing is generally increases in rainfall, especially in the areas where it's already raining the most. There were some storms that had some pretty interesting spatial signatures in the changes in rainfall. In particular, Irma and Maria had really concentrated increases more towards the center of the storm, but some drying in the outer regions. And so, this kind of thing can, again, really have some impacts if we're thinking about, localized flooding as these hurricanes are making landfall. So here, again, this is a kind of heat map synthesizing the results for the precipitation. And here, we're pretty much seeing green everywhere. So I would say we're getting a robust increase regardless of what future scenario we're looking at. And in some of the cases, this is the increases in precipitation are exceeding what we might expect based on simple thermodynamic arguments, namely Clausius-Clapeyron. Okay, so this is the last plot I'm going to show. This is also looking at extreme rainfall rates. So this is, I think, hourly precipitation. So this is PDFs. Here at the top left, we have Hurricane Katrina. These are the 10-member ensembles for, the pre-industrial is kind of hard to see, but in blue, black is historical, and red is going in the future. And essentially what we see, if we look at the ensemble averages, which is here on the right, for 3 kilometer, that's the solid lines, we're seeing systematic increases in the probabilities of extreme rainfall events going from pre-industrial to historical to RCP 8.5 at the end of the century. We're also seeing that regardless of whether we've got 3-kilometer resolution or 27-kilometer resolution. And this is something that is robust across the hurricanes that we looked at, so Irma and Maria. All right, so some concluding remarks. I wanted to talk a bit about designing these storyline experiments. And so, as I mentioned, there are a variety of methods that are suited for different kinds of questions. And here we use this approach where we're doing hindcasts with a convection-permitting regional climate model. And I kind of wanted to just go through some of the thought process as I'm setting up these simulations so that, if people are interested in running these for an event that may have affected their region, there are a lot of things to consider just in, setting this up. They mostly fall into the kind of categories of physical processes and how to balance the supercomputing power. So one consideration is, the hindcast quality. So, we do want to try to be able to get tropical cyclone intensity, which these simulations did pretty well. Rapid intensification is still a challenge. If we're thinking about physical processes, ocean coupling is one that I've been thinking about a lot. And this is also one that I think this so far has been a challenge, but I think that this is where we need to go into the future. So there's been some work led by Ben Timmermans, where he's looking at, he's using the data from these simulations to force an ocean wind wave model. And what he's finding is that the lack of coupling can actually produce tropical cyclones that are too strong, and the ocean wind waves are too strong. On the flip side, if you have overly strong ocean mixing in the coupled model, then that can also produce errors in tropical cyclones, but then they become too weak. And so this is something that we really need to work towards because, as I mentioned, there are a lot of feedbacks that are important for determining tropical cyclone intensity that come from the ocean. Another thing to think about is the choices of the global climate models that provide the climate change perturbations. As I was mentioning, they get added to the hindcast. And really, in thinking about that, it's useful to put those climate models in the kind of context of, where do they fall in the range of climate sensitivity. And so, the model that I used for the perturbations is a little bit lower in the range of climate sensitivity. And so what that means is that the estimates that I showed are perhaps more on the conservative side. And so, if you have the computing resources to run with maybe 2 or 3 of these, it would be good to get some, spread across that. And also, it may be, even more complicated than just climate sensitivity. We've got changes in sea surface temperature gradients across basins and things like that. Then model resolution, how much is enough? For my simulations, I actually didn't show this, but I did one of Katrina that was down to 1 kilometer resolution. And in that case, I wasn't seeing much change in the hurricane intensity. So I thought, okay, well, 3 kilometer is enough. And then actually, I wanted to run a bunch of hurricanes, so I kind of bumped it up to 4.5. So that's another thing to consider. Parameterizations, in this study, we're going down to no convective parameterization. But we also have to think about microphysics, PBL, and then ensemble size. This is something that's also important where we have to think about having at least a big enough size that we can say something with statistical significance. So I think for the sake of time, we kind of already saw this part, but I just want to mention that the data from these simulations is online at this portal. And I'd like to thank the symposium organizers and University of Miami and the sponsors for making this happen, as well as DOE and NERSC for supporting this work. Thank you.
Thanks, that was really fascinating. Oops. Great. Thank you. Wait, we have time for one question. Don't go away. I think we have one question from the audience. I see people are starting to write in Slido, so that's good. Remember to put the name of the speaker if it's for someone specific. Does anyone have one question for Christina before she sits down? Yes.
I was just curious about, thank you. And perhaps you captured it in the summary statements, and then I'm not making the connection.
Sure.
But in one of your later slides on the model results, you had showed that under the 8.5 scenario, I guess, that the intensification of rainfall you noted seemed to surpass what would be predicted based upon kind of thermodynamic rules. And I was just wondering if that caused you to think that it's falsely, or creating the intensification, or it underscores the fact that there are other factors that are driving intensification. So I just wondered if you could elaborate on that statement, please.
Yeah, that's a really good question. Are you guys able to hear me still? Yeah, that's a nice question. So I would say that, so this is something that we're hoping to dig into some more, but the working hypothesis is that there are some physical processes at work beyond the kind of simple thermodynamic arguments that people use as sort of a first guess. So there may be some changes to, the dynamics of the storm, the sort of wind fields and vertical velocities that may be contributing to that.
Thanks. Okay. Really interesting stuff.